Okay, so if you go to Canvas, Files, you'll see Dry Lab 6A and 6B. You're going to do that one for those two in lieu of the one in your lab packet. The reason for that is I want you to focus totally on balancing equations. That's very, very germane to chemistry and almost all aspects till you get to biochemistry and organic. Then there's equations, but they don't ever balance them. I don't know why. So in general chemistry, it is like the supreme law of the land. Balance the equations. If in doubt, check it. Do an inventory. Blah blah blah. Whatever. So that's what the 6A and 6B is. It's focusing on just balancing equations. And I gave you the answers. So you have a choice of prepping. Remember, the purpose of this class is for prepping for your next chemistry class. So you have a choice on Lab 6 to either just do the answers given and turn it in, or you can actually balance the equations for practice. Unit 4 starts off with something called stoichiometry. First step of stoichiometry is balance the equation. If you cannot balance the equation correctly, the whole problem is wrong. And there are 5 steps to a stoichiometry problem. Actually, let me back up. There are 4 steps, 5 steps if there's a limiting reactant, which we'll talk about when we get into unit 4. My point, though, is it's crucial you balance equations. So that's the whole focus of 6A and 6B. Okay, does that make sense? And then scan those and submit it as one file. Okay. All right. Any other questions about? Yeah. How do you find it? Canvas files, lab related. Oh, let me do one thing. I have to sync it. Thank you for asking. What this is doing is, because I have 2 lab sections, the system won't let me put them together because of some confidentiality issues. So what they provide is something called a blueprint, which allows me to link 2 lab sections together for doing most things. I can't grade together, and I can't do mail together either. So, but whenever I change the blueprint, I have to sync it with the 2 lab sections. Can you see it there now?
Files. Oh, yeah. Another 16. Yeah.
Okay, cool. All right. Does that make sense on the lab 6? So we're going to focus on lab 7 today, and tomorrow on single displacement reactions. So there's, guess what the first step is? Balance the equation. Also, I've been getting emails from you regarding can't find some of the videos. And some of you have been using my YouTube channel and the dates to find videos, which works most of the time. It's better to go to modules. And sometimes if I have a glitch on the video that day, I will get last semester's version of it, and I have to change the date. And I don't change the date of the original video. I change the date of the one that shows up in modules. Okay, so use modules. And if it doesn't work in modules, then go to the YouTube channel, but try modules first, always. I try to keep that as updated as possible. All right. So just a quick review on equations. Equations involve reactants and products plus energy. Occasionally, you'll see the energy on the left. Most reactions, it's on the right. If it's on the left, that means it requires energy to work. Those are called endothermic reactions. If energy is given off, it's called exothermic reaction. Thermic meaning heat, exo meaning leaving. Okay, if a reaction is going to happen, it starts with something unstable wanting to become more stable. That's the theme I fall upon in every single chemistry class and molecular biology class that I teach. Unstable to stable, otherwise it's not going to happen. The more stable the product is, the quicker it'll happen. Okay. For reactants to become products, the bonds of the reactants have to be broken first, and that requires a little bit of energy. The size of that energy determines how fast the reaction will go. And I gave this example last time, but charcoal and diamonds have the same formula. Carbon, it's all it's in a diamond, it's all it's in charcoal. And they sure as heck don't look the same. Charcoal is more stable than a diamond. Everyone goes, what? So a diamond will eventually return to charcoal. Takes a long time. The reason why it's so slow, it's incredibly slow. I'm talking like 1 million years. That's how long it takes to create a diamond. It's because the activation energy is horrendously high. Because the activation energy, which starts the reaction, is so high, that's why it's so slow. But charcoal is more stable than a diamond. To me, when I first heard that a long time ago, I went, you got to be kidding. I mean, charcoal you can crunch in your hand, not a diamond. It's all how the carbon attaches to the next carbon over. That's all it is. And the carbon, it's a very, very, very stable connection. With charcoal, it's very loose. I mean, you've seen charcoal, crunch it in your hands. Okay, so we're going to have about 4 or 5 different kinds of reactions. The one I'm going to talk about today is called a single displacement or single replacement reaction. Are there any questions about the generic reaction itself? Okay, so let's whip over to now in a single replacement reaction, it involves a metal plus a salt. And the salt's composed of a cation and an anion. If a single replacement reaction goes, the metal is oxidized and the salt is reduced. So what do I mean by oxidation? I'm sure you've heard this a lot. If you cook at all, for example, if you make apple pies this time of the year, what apples do once you peel them? Who cooks? What do they do? And what do they look like? They're all brown. And that's an enzymatic oxidation. So one of the ways you can keep them underwater, protects them from oxygen, but they bruise. Now, so most people in rust, iron turns to rust. That's another oxidation process. Very, very common because we're in an oxygen environment. That's where that word oxidation comes from, because oxidation is the oxidizer that converts O2 to something else that's more stable. That's why when you find a metal in natural circumstances, it's always an ore, O-R-E. And the ore is the oxidized state of the metal. For example, iron. If you leave iron in your backyard, after a week, you get rust. And that's the more stable form of iron in our atmosphere. That's why it does that. Uranium. You don't get uranium you get uranium oxide. So you have the uranium ore that's converted to uranium, and then it goes through another process to get weaponized uranium. But my point is, metals are always oxides in nature because they're more stable. But what is oxidation? Oxidation is the loss of electrons. For example, I've been really phlegmy. I'm allergic to something in the fall. I've been sneezing a lot. Anyway, okay, so oxidation is a loss of an electron. Now, when you look at that, it's important to make sure that the charge, now the metals charges are all zero. In my class, whenever I have a metal, I always put a 0 as a superscript. Your next chemistry class probably is not going to do that. Also, your book doesn't do that. I do it so you know it's a metal. Sometimes they'll put an S there. Also means solid metal. Okay, notice on the left, the charge is 0. So the charge on the right also has to be 0. So we have 1 electron leaving silver. So that means that's a charge of -1. So the charge on the silver is +1. If we lost 2 electrons, then the charge on the metal would be +2. Now, this is called a half reaction because whenever we have oxidation, we have to have simultaneously reduction. So in other words, when something's oxidized, it gives off an electron. Something's got to receive that electron. So we have a donor and a recipient. So receiving electrons goes on the left. Donating electrons goes on the right. And this is also called a half reaction. This is the other side of the oxidation reaction, is a reduction reaction. Now, what has to balance are the number of electrons. If this reaction involves iron and silver, iron, this is the salt now, like iron 2 sulfate or something like that. If this gives off 1 electron and this requires 2 electrons, we've got to do something about the reaction above. So what we're going to do is we're going to multiply the reaction above by 2 to kick the electrons up to 2. But what we do to electrons, we have to do to the salt, the Ag+, and also the metal. So everything gets multiplied by 2. Then when we add these 2 together, we're going to end up with electrons are canceling. 2 on the left, 2 on the right has to be equal. No exceptions, which is nice. Okay, and I notice I said won't happen. Okay, sometimes single replacement reactions work, and sometimes they don't. And it has to do with something called an activity series. Now, all those are metals except for one of them, and that is this guy here. So in terms of single replacement reactions, I want you to treat the H2 like a metal. Okay, so this is the activity chart. And activity means some of these reactions are much more stable than others. The higher in the list, the more stable they are. So the first thing to do in our reaction is to find iron and silver. Okay, so this is the rule to figure out whether these reactions are going to work or not. Find the two elements on the activity chart. If the metal is above the salt, the reaction happens. Now, in this case, iron is above silver. Silver is the metal. Silver is below iron. So that's why I put an X there, that it doesn't work. So the easiest way, just remember, the metal part of the reactants has to be above the salt, the ion, okay? Now, when you get into 1A particularly, or 1B, or 1B, I forgot which one it's covered in, they're going to talk about why that's so. And basically it has to do with stability of the ion versus the stability of the metal. If an ion is super stable and it's easily oxidized, in other words, losing electrons. Okay, so we look at this reaction here. We have aluminum, metal, notice the 0, or we can have an S there, plus iron 2 sulfate. Is that going to happen? Well, first thing we need to do is figure out what the reaction is first. So in other words, so if this reaction was to happen, we're going to have aluminum going to plus something. So if you look on your common ion chart, aluminum goes to plus 3. And then iron is going to go from plus 2 to iron metal. Now notice that sulfate, the SO4, I haven't talked about. So in the single displacement reaction or single displacement reaction, you always have a spectator ion, and it's usually a negative ion. Spectator ions just right along for the ride, just like a spectator at a basketball game. You have players and spectators. Spectators do nothing in terms of the game. Players do everything. Same with chemical reactions. A spectator ion just cruises right on through, unchanged. So the sulfate comes through on the aluminum, because now aluminum's positive and the sulfate is a -2. Now, what's wrong with that so far? AlSO4. Now think about your naming conventions. Remember, if it's ionic, has to be neutral, net zero charge. It's not net zero now, is it? Plus 1 over. So we're going to take three SO4s because they're -2 and 2 aluminum aluminum 3 plus. So that means +6 -6. Okay. All right. So the question is, will this reaction work? First of all, it's not balanced. Let's balance it really quickly. Okay, we have 2 aluminums here, 2 aluminums there. We have, let's move the iron over here. It's a little cramped here. Okay, we have 1 iron on the left, 1 iron on the right, so that's okay. We have 3 sulfates on the right. Now we have 3 sulfates on the left. 3 irons now, though, so I need to put a 3 here so it's balanced. Okay, so now the question is, this going to fly? Now, if you do the half reactions, you end up with the same result without the spectator ion. If you balance it first, you don't have to do the half reactions because it carries the spectator ions with it, the SO4. Okay, so now we need to find aluminum and iron on that reactivity chart. Okay, so here's aluminum. And there's iron. Now, the reactivity chart will tell you what the ion is also, without having to go to your common ion chart. Okay, so which is the metal in that reaction? Is it the aluminum or iron? Aluminum. So where is aluminum in relation to the iron? Is it above or below? Above, so that works. Metal is above, the reaction goes. So this will be a viable reaction. And then so that's the trick. Once you, number one, balance it. So single replacement reactions, the iron becomes an ion, the salt becomes a metal. Now we're going to see tomorrow we have double replacement reactions. There's no metal involved at all. So if a metal is involved, think single replacement. And the question is the metal going to be oxidized? Question mark. That's what the reactivity chart is all about. Now, today in lab, you're going to be given a whole bunch of combos. And you're going to see if the reaction happens. Then you're going to look at the reactivity chart and you can predict whether it will happen or not. Now, sometimes the reaction happens, but slowly. So instead of no reaction, you write no visible reaction, NVR rather than NR. So today and next week's wet labs are really fun. Color changes and everything, bubbling, and they're quick too. Just going to go click, 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 click. Write down the results and then correlate it to reactivity charts. Okay. All right. Does this make sense? Okay. So step one. balance the equation. And then, okay, convert the metal to an ion. So you look on your activity chart and find the metal. It'll tell you the ion. And then convert the ion to a metal. So balance the equation. Now to do that, because you're not going to get the results of the reaction, you have to predict what it's going to be. So you convert the metal to an ion, and it'll show you on the activity chart. You convert the ion, I call it a salt, convert the cation to a metal based on the activity chart. Step number one. Step number two is find the metal on the activity chart in relation to the ion. If the metal's higher, it's going to happen. If it's lower, it's not going to happen. So you can practice this a lot today in lab. So let's do a couple more of these. Okay, do these steps make sense? Reasonable? Everyone say yes. All right, so let's look at this guy here. Let me okay, so we have zinc metal and ferric, excuse me, iron 2 oxide. Why is it iron 2? Why not iron 3? What's the charge on O oxide? -2, yeah. That's why forces the iron to be +2. Again, that's another weak point in incoming 1A and 2A students. Nomenclature. Okay, so if it's ionic, you got to balance the charges. Okay, so we've got, and that's a form of rust, by the way. It's not the common form, but it's a form of rust. So basically, if we have zinc and rust in water, is anything going to happen? Okay, so first thing we're going to do is we know that that's a +2 because the oxide's a -2. All right, first thing we need to do is balance this thing. Can we change the zinc to an ion? And we change the ion to a metal. Okay, so what charge does the zinc go to? If you look in your reactivity chart, it'll tell you. zinc goes to +2. Okay, so on the left reactant side, the zinc is the metal because of the superscript 0. The iron is an ion. So the question is, on the activity chart, which is higher, zinc or the iron? Yeah. It doesn't. It's -2. That's why the iron is +2. The nonmetals on the top left usually form negative ions. Okay, so which is higher, zinc or iron? Zinc. Zinc's the metal. So that means this reaction happens. Now we need to include the spectator ion, which in this case is going to be the oxide. We're going to have zinc metal plus iron 2 oxide gives us zinc oxide plus iron metal. What's the spectator ion? What does nothing? What doesn't change? Oxygen. So oxygen spectator ion. Now we get the double replacement. I'm going to ask the same question. What are the spectator ions? You'll frequently have one that doesn't change. Or a double replacement, frequently it's 2 spectator ions or 4 spectator ions or no spectator ions. Goes in 2s. The most common is 2. Okay, so did that make sense? Why this reaction goes? The metal is higher. Now, if you look on the practice tests, I gave you a reaction and I asked you if the reaction is going to go and why. 2 points, yes or no, and 8 points, why it'll not go or go. Okay, so any more questions on that? Let's do another one. Let's throw in some hydrochloric acid. Okay, so the HCl is an acid. And the definition of an acid, which is unit 5 stuff, basically is acids will give off a H plus ion. Not H negative, H plus, +1. By definition, that's an acid. There are strong acids and weak acids, and we'll talk a lot about differences between those when we get to unit 5. But for this lab today, you're going to need to know that HCl is an acid and it gives off H plus. So the weird part is you're going to treat that like it was a metal. So you're starting with zinc metal. Zinc metal, and the ion in this case is going to be H plus. Okay, so the H plus is the ion, the zinc is the metal. Question is, which is higher on the reactivity chart? Well, let's balance it first. When we balance it, I'm going to swap out the metal for the salt. So in this case, it's going to be zinc 2, and the H plus goes to hydrogen gas. So is that balanced? No. We need two H's. We haven't, what's the spectator ion? Chloride, right. Okay, so now we're going to add in spectator ion. That's going to be okay. So which is higher? H2 on the reactivity chart or zinc? Look on the reactivity chart. You're on the wrong page. Yep, this one here. Which is higher? Well, offhand, I don't know. I have to look. Since no one's venturing a guess. Okay, so we have H2 here, and where's zinc? Zinc's up above. So we have H plus here. So zinc's a lot higher. So that means what? The reaction is going to happen. And then the Cl, the chloride ion is a spectator ion. Now, I also have lots of extra practice on single and double replacement reactions on Canvas under files as well. But do the lab first. And if you feel you need more practice, go to lab files, lab related, and you'll see quite a few worksheets on practicing this. It's just a matter of doing a whole bunch of them. Notice I have a common structure in this class. Lots of repetition. That's the way I learn. In fact, I was learning this morning a tune by Jerry Lee Lewis, Great Balls of Fire. And I was looking at the intro, and intro is really simple. It's amazing how simple it is. I'm going, wow, I could probably learn that without having to look at the sheet music. But I have to play a song about 300 times before I can memorize it. I'm terrible memorizing. And I've never been good at it either. It's not because I'm old. Certainly oldness comes into play, but still, I was never good at memorizing stuff. Okay. So that's it on single replacement reactions. Let's see. And those are all the examples I gave. Any questions about this? Yeah.
The top is the reactive.
Yeah. Yeah. The higher you go, the more reactive they are. So you find the metal and the salt. If the metal's higher, it happens. If it's not, it won't happen. Yeah. It's usually the negative ion attached to the metal ion. Usually. I would, in this class, I'm trying to think of an exception. I think you can say 100% of the time. Now, that's not true tomorrow, the double replacement. But with single replacement, because normally we work with metals, when they form an ion are always positive. So then you have to have something that goes with the positive, which is usually the spectator ion, and they're negative. So, good question. And it's usually one also. Double replacement, you can have 0, 2, or 4, and it's usually 99% of the time 2. Okay, well, I'm going to end this here. And